Hello, good afternoon, everyone. Please welcome Sanjana Kandi, Systems Software Engineer at NVIDIA. She is going to talk to us about AI with a conscience, building fair and transparent systems in Python.
Thanks for the introduction, and thank you everyone for being here, especially this late in the day after what I'm sure has been a marathon of great talks. I'm Sanjana, a senior system software engineer at NVIDIA, and I'm really excited to be here today at my very first PyCon. Today, I want to talk about something that doesn't show up in error logs, but still causes real-world problems: fairness in AI. It's messy, it's important, but yes, we're going to kind of talk about Pi, and we'll see how that goes. Before we get started, I want to give a special shout out to Katrina and Jeremy, if they're here, who's been mentoring me as I prepared for this talk. Thank you so much, guys. We're going to talk about a bunch of things, starting from setting some context, talking about fairness metrics, methods to mitigate bias, a hands-on or a walkthrough exercise on a real-world example, as well as some takeaways. All right, before we get started, let's do a quick show of hands. How many of you here have grown up with a sibling and definitely argued about who got the bigger half of a pie? Even when it was split exactly in a half, did you ever find yourself thinking, is this fair? Because I know I did, and looks like a lot of you here thought about the same too. That's the thing about fairness. It's not easy to define. And it could mean different things for different people. Let's zoom out for a second in this context. Imagine your parent who's baking the pie. Should they have gotten the better half of the pie because they were the one who were putting in all the hard work? Or should the hungriest person have gotten the bigger slice? Or maybe you should have gotten it because you were a kid and you didn't know how to bake one, right? So is this question of, is this fair, can have a lot of different answers depending on who you ask. And when we build machine learning models, those are the same questions which come up, but just with much bigger consequences. With the rise of machine learning and AI and the powerful GPUs which are fueling this revolution, ML models have become deeply embedded in our lives, starting from shopping recommendations to loan approvals and even hiring decisions. ML models can come into play in all these scenarios. And if we're not careful with these models, they can reinforce the very biases and inequalities that are already present in the data that they learn from. And this isn't just hypothetical. There are a lot of scenarios where we've seen how these biases show up in the decisions. For example, a large tech company tried using an AI model to rank job applicants. And it ended up discriminating against women because it reflected the training data which had the past hiring biases. This wasn't malicious, but it was mathematical. So bias can creep in through many channels. It could be historical, label, representational, proxy variables, and feedback loops, some of which we're going to talk about today. Now, we'll start with a simple base case to ground our discussion, and then we'll keep coming back to this example and explore different aspects of fairness. And this base case goes like this. Imagine a school district which implements a machine learning model to recommend students for an advanced computer science degree program. The model is trained on multiple attributes on historical data. It could include student past grades, activity involvement, attendance, and so on. Now let's start exploring the sources of bias. Firstly, historical bias. Historical bias occurs when model learns from past decisions or patterns that reflect existing inequalities, biases, and prejudices. It could be intentional or non-intentional. Let's go back to our use case. In our use case, it's possible that smaller schools or less well-funded schools have fewer nominations to this advanced computer science degree program because teachers weren't familiar with this program, whereas candidates from a well-funded school may be may have more nominations to this program because they have more resources to information. And how this affects the model is that the model identifies that the students of well-funded schools are more likely to be selected, which reinforces these existing inequalities, even if the other candidates from other schools perform equally well. This scenario illustrates how historical biases become embedded in the training data and highlights why we need fairness-aware practices. Label bias. As you can see from the picture here, if you ask the person on the left, he might identify this image here as 6, but the person on the right might identify here as a 9. So what this essentially is saying that label bias can happen when labels used for training, in our example, if a student is selected or not selected, are themselves flawed. And this could be due to human bias in previous selections, it could be due to inconsistent or subjective evaluation criteria, or even administrative oversights. And when we have students who were qualified, who were not selected in the past, not being reflected in the training data, these incorrect decisions become a part of the training data. And in future, the model treats these wrong labels as ground truth. As a result, it learns to devalue the students who shared similar characteristics to the ones who were previously overlooked, even if they're well-deserving candidates. This is why bad labels perpetuate bad predictions, and not because the model is inherently biased, but because it's taught to trust flawed historical decisions. Coming to representational bias, this happens when certain groups are underrepresented in the training data, and this is probably the most common kind of bias that we can find. The model lacks enough examples to learn patterns, as a result of which it generalizes very poorly on these groups, even if they're just as capable. This is again not about bias labels or historical trends, but it's about data quantity and diversity. Now, in our example, very few students from underrepresented districts or less well-funded schools may be present in the training data set, because of which the model may not see enough examples to understand their success factors. And it performs poorly by predicting lower scores for such candidates. And it often ignores unique indicators of success, like overcoming resource limitations, for example. And when we keep having such biases in the data, it creates a feedback loop, and we're going to talk about this in the next upcoming slides. Proxy bias is when, this may not be very explicit, but this is when we have certain attributes or sensitive, we might have certain attributes which are correlated to sensitive attributes in our data set. For example, in our use case, the model may not use certain attributes like socioeconomic status or parental income explicitly, but it may use features like school type, which could be public or private schools, number of extracurriculars or AP courses availability, which often correlate to higher socioeconomic status. And the model learns to favor certain candidates over the other. For example, it may learn to favor private school students indirectly over public school students, even though the socioeconomic status attribute is not used in the data set. In this case, private or public becomes a proxy variable for wealth and privilege. Feedback loops. The model keeps, as we see from the picture here, the model keeps reinforcing its initial bias, which leads to even fewer students being selected in future. So if we have an initial biased model which already performs poorly on students, say, of certain schools, then this may impact the behavior of students in different ways. For example, social consequences, where looking at the lower selection rates, fewer students from these schools even bother applying in future years. And what's the consequence of this? It leads to data consequences where fewer applications or less data from those schools are seen in future training cycles. Because of this, there are also model consequences where the model continuously learns to learn from this increasingly skewed data set, which reinforces the bias again. So essentially, bias amplifies over time in circles if we don't intervene. So as we see from this example, bias can sneak in from different directions even if they're not evident in plain sight. And we'll be talking about a Python-based library called FairLearn, which provides a powerful set of tools to evaluate and mitigate fairness issues in machine learning models. Firstly, I'm going to be talking about demographic parity or group fairness. So this fairness measure states that the probability of a model predicting a positive outcome should be similar for all subpopulations which are distinguished on protected attributes. What this means is that in our example of school recommendation system, a school district must recommend students to the summer program at a similar rate for group A demographics or group B demographics or group C or so on. But what this does not talk about is that if the person actually qualifies, and it's only looking at fairness from an equality perspective. And when we look back at the pie example, what this means is that you, your sibling, your parent, or anybody in the room should have gotten the same amount of pie. From a mathematical perspective, we say that the probability that the model predicts a positive outcome for group A must be same as the probability that the model predicts a positive outcome for group B, or so on. And FairLearn provides demographic parity ratio and demographic parity difference as the fairness metrics that we can use to calculate this measure. The demographic parity difference measures the absolute difference between the highest and the lowest selection rates. And if we have to give an example, if, say, private school students are selected 40% of the time, and public school students are selected 25% of the time, then the difference here is 0.15. But we need to make sure that we're enforcing a near zero constraint here, which means that a value of 0 means perfect demographic parity. On the other hand, demographic parity ratio measures the ratio between the smallest and the largest selection rates, and we want this to be closer to 1, because the ratio has to be closer to 1. And this shows severity in disparity, and it's a better metric to use when there are more than 2 classes. So this metric is intuitive and fairly straightforward to compute and gives a good baseline to understand the model. However, demographic parity, if applied blindly, can lead to something called allocation harm, where opportunities are equally allocated without regard to the accuracy or the outcome itself. And that's why we're going to explore the next metric called equal opportunity, which takes into account the qualification or the accuracy. So equal opportunity is a fairness measure to ensure that the machine learning model performs equally well for different groups. So in our case, the school district must ensure that they recommend the same proportion of qualified students from group A and same proportion of qualified students from group B for the summer program. So if 10% of qualified students from group A are selected, we must ensure that 10% of qualified students from group B must also be selected. From a mathematical perspective, we can use FairLearn to calculate the true positive rate, which is basically the ratio of correctly predicted samples versus the actual positive samples, to understand equal opportunity metric. However, this metric only looks at the deserving positives. What about the flip side, where the model must ensure that it isn't unfairly giving undeserved positives or making errors evenly? That's where equalized odds comes in, which is a bit more stricter, and it covers both sides of the prediction, which is positive as well as the negative. So equalized odds, again, by definition, is a criteria that ensures that the model treats different groups similarly in terms of true positive rates as well as false positive rates. In other words, the model should be equally good at identifying qualified students, but also equally cautious in avoiding false positives for unqualified students. So we can use TPR and FPR, and also use equalized odds difference and equalized odds ratio, which is similar to the demographic parity difference and the ratio we saw earlier. And the good thing about this metrics is that it ensures benefits and errors are equally distributed, but achieving equalized odds is fairly difficult because it must align to two metrics, that is TPR and FPR, across all the groups. But often there are trade-offs like a small accuracy drops, which may be required to ensure that this particular metric is satisfied. Now, Now let's go through the mitigation strategies that could be applied to address this problem. So we can have mitigation strategies as a pre-processing algorithm, in-processing, or post-processing algorithm. We're going to talk about exponentiated gradient, which is a very powerful algorithm to mitigate bias in classification while maintaining accuracy. And what this does, or how it performs, is kind of like a two-player problem, where player one, you can call them learner, which tries to minimize the prediction error. But player two, you can call them the fairness auditor, which tries to enforce fairness constraints. So that could be equalized odds, demographic parity, or equal opportunity. So how this works is that suppose we want to find a classifier that minimizes some loss or error, but also satisfies a fairness constraint. Then rather than training just one model, we want to train a set of models. It could be 1 to n, and each model is trained using updated sample weights that penalize for unfairness. And the final predictor that we get is a weighted mixture of multiple models. Grid search, on the other hand, it's also an in-processing algorithm, but unlike exponentiated gradient, which adapts during training, grid search takes a much simpler but exhaustive approach. It trains many models under different trade-offs between fairness and accuracy, and then picks the best one. It's pretty straightforward because at one end of the spectrum, you might have a model which is really good with accuracy, but it's doing the worst with respect to fairness constraints. But on the other side, you might have the complete opposite. And in between, you have multiple models with different accuracy and fairness. And we basically want to pick the best one, given what our use cases and what thresholds we're going to enforce the fairness to be. And the advantage is that you don't need to tune for step sizes or learning rate, and it picks the single best model and helps to visualize the trade-offs between the fairness and accuracy. But one possible limitation here is that it trains too many models, especially with large grids, which could make it much slower compared to exponentiated gradient. The last one here is a post-processing algorithm called threshold optimizer, which basically takes a trained classifier. It could be from a logistic regression classifier, random forest, any classifier which gives a binary, which is basically a binary classifier, and it adjusts the decision threshold separately for each sensitive group after the model is trained. So it does not change the model's scores, it just changes the thresholds which are used to convert these scores into labels. So its final prediction is essentially based on the adjusted threshold for that particular group. The advantage of threshold optimizer is that there's no retraining of the model required, and it works with any classifier that outputs scores. We'll go through a small demo of the same problem that I just spoke about. So in this notebook, we'll explore the fairness in ML with the same situation of recommendation system that selects students for a competitive computer science program. And we'll again consider this with respect to public versus private schools, and we'll use two definitions: demographic parity to measure fairness metric, as well as the equalized odds. And we'll also apply the mitigation using threshold optimizer and see what results we get. So starting off with the first cell, I import a bunch of things. These are NumPy, pandas, and a couple of things which you need for training a model. From FairLearn, I'm going to import what we just discussed, the threshold optimizer object, demographic parity difference, equalized odd difference methods that it provides. And we'll simulate a student data in such a way that this shows the bias we just talked about. So we'll have, say, 1,000 samples of student data, and we'll have multiple attributes like GPA, math scores, test scores, competitions. We'll also have the school type, because this is exactly what we were talking about with respect to proxy variables. That's we'll have public and private schools. And to enforce a slight bias, we'll also have private school students getting a little more advantage in terms of the score. And to enforce label bias, we'll also try to flip a random 20% of the labels of the public school type. So the data set looks something like this. You have 5 attributes, and then the last column here is the label, which is recommended or not. Then we do a train test split where we have the X and Y. X is the features that we're taking. So we're going to drop the school type column because we consider that as a sensitive feature, and we're going to keep the rest of it. And Y here is the label, which is only the last column here, which is the recommended or not to the program. And we'll do a train test split, 70% of it being the training set and 30% of it being the test set. Now, we'll start with training a baseline model, which uses logistic regression. So we'll apply logistic regression, and we'll try to get the baseline accuracy per group, as well as the demographic parity difference and the equalized odds difference. So as we can see from the outputs here, we see that the accuracy is very high for school type of private versus accuracy is comparatively low for public. So the model doesn't do a good job in predicting candidates from public school, as well as it does for candidates who are in private school. And we see an important baseline metric here is the demographic parity difference and the equalized odds difference, which shows 0.3, about 35 to 37% for each of them. So from what we saw earlier, we want this to be as close to 0, and this clearly indicates that there is demographic parity bias as well as an equalized odds metric, which is being violated here. And when we look at the selection scores, what we can see is the private schools have a selection rate of about 75%, whereas public schools have a selection rate of about 37%. So there is a vast difference in the selection rates between both the groups. So let's keep this as the baseline and move on to apply demographic parity as our first measure. So we will apply threshold optimizer with the constraint being demographic parity here. And then when we recalculate all of these metrics, we see the accuracy might have dropped a bit, but let's focus on the demographic parity difference after we apply this mitigation, which is reduced to 0.04 from 0.3. This is a big reduction, and what we can see with below in the graph here is that the selection rates for public school and private school here are almost the same. So when we compare it to the baseline, the selection rate, the blue indicates the baseline, and then the orange indicates after mitigation. So we see that baseline had a huge difference in private versus public, but then after mitigation, we see that both of them are approximately the same. So in this way, we are making sure that the demographic parity constraint is more or less satisfied for this particular use case. Similarly, we'll also apply the second mitigation, which is the equalized odds. The code is pretty much the same. We just have to change one small part of it where instead of demographic parity, we add the constraint as equalized odds here. And we, again, do the same thing. We get the accuracy per group and the equalized odds difference after mitigation. And we see that the equalized odds difference has also reduced, and the accuracy per group also is comparable. Now, when we consider the true positive rates and the false positive rates, baseline versus after equalized odds mitigation, I will scroll all the way down to the graph because that's a better visualization. We see that the true positive rates had a bit of a difference initially, but after applying the mitigation, we have reduced it and tried to make it comparable. Same thing with the false positive rates here. The false positive rates was actually 0 for private schools before in the baseline, but then that could have been the perfect scenario, but sometimes perfect doesn't work all the time, and because equalized odds takes true positive as well as false positive, it could be a little difficult to have both of these reduced to 0. So we can either keep one of them to be 0 and then optimize for the other, or we can set the thresholds manually to ensure that it satisfied whatever constraint that we're looking for. All right. To close, I would like to say fairness isn't automatic in machine learning models. It's something that we have to build in intentionally. And bias can enter at any stage. So interventions need to happen either before training, during training, or after training. And we just learned how we can use different fairness metrics as well as mitigation strategies from FairLearn to make sure that we're building fairness-aware models. And remember, fairness depends on the use case. What's fair in hiring may not be the same in healthcare or education. So there's no one size fits all. And finally, fairness isn't just a technical issue, it's a human one. It requires engineers, domain experts, policymakers, all at the table to be present when we're talking about this. So the call for action is simple. Make fairness a checkpoint, think about impact and just not accuracy, and build systems that reflect values that we want to see in the world. Thank you. And
all right, we have 3 minutes for questions. So if you have any, please walk up and make lines behind the microphones and speak into them.
Thank you for the amazing talk. I have a quick question on the 2 mitigation strategies you have talked about. One is exponentiated, another is called the grid search.
Yeah.
From my understanding, the difference between them should be one have more models, but only picks the best, but another takes a weighted average among many models.
right.
Yeah, so my question is just, what makes it not possible to combine those 2 approaches? We can both have a lot of models and also take the average. Thank you.
I think that's possible, and we can do that. But I'm not sure if FairLearn directly has any class or which implements this. But I think what you're saying is a valid consideration.
Thanks.
Does the FairLearn framework work with all types of models, or just like classifiers, regression type problems? Does it work with like LLMs or things like that too?
No, it doesn't. Right now it works with classifiers and classifiers and regressor models. LLMs, because it's a generative model, it might not work with FairLearn, but then FairLearn does provide an option to have your own algorithm in place. So maybe if there is a way where we can have a binary classifier with LLMs, we can add that and have a human feedback there, which will, again, send this inputs back.
Got it, thanks.
Yep.
All right, since there are no more questions, I'd like us to give another round of applause to Sanjana Kandi.